All right, let's take a look at how to divide radicals. I'm actually going to call it rationalizing denominators because we're not actually going to be doing division. Now, if it does look like a division problem, you can indeed simplify. Like something right here, I could rewrite this if I wanted to as one single root of x to the third over 5xy. And you can just simplify it as if you're simplifying a normal fraction. For instance, this 1x is going to go into this one here. It'll take one away from the top. So what that would turn into is a square root of x squared on top over now just 5y. But the reason I also call it rationalizing denominators is because if I rewrite this where I have it split as x squared over the square root of 5y, I still don't love the problem because I still have a radical in the denominator, and it doesn't make sense for me to divide by an irrational number. So we want to turn this irrational number into a rational number, which is not a square root value. Now we can do that without changing the value of the equation if we simply multiply by 1. You can multiply anything by 1 and it won't change the value of the equation. Now I'm going to draw a line right here just to break it up because we kind of already did the division over here. But what I want to do now is rationalize. Now, I'm not actually going to be multiplying by 1. I mean, the value is a 1, but what I'm actually going to multiply by is a fraction that the top and the bottom match. Because remember, as long as you take something and divide it by itself, it will always be 1. Now, how do you pick what goes in that fraction? Well, I just look at what is currently in my denominator. It's a square root, so like a little 2 there, which means if I have the exact same square root, I've kind of created a pair of values. I'm making it be a perfect square. 5 times 5 is 25. Y times y is y squared. That's a perfect square. So if I mimic what's on the bottom here over here, and then I also put that same value on the top, well, the square root of 5y divided by the square root of 5y is 1. I'm going to take this entire equation and just multiply by 1. So it's not going to change the value, but watch what happens. I'll go ahead and do the top. Multiplying radicals means that you just multiply everything on the inside as long as it's the same type of radical. So notice I get 5x squared y. And then what about the bottom? Well, I already kind of said 5 times 5 is 25. The square root of 25 is 5. And y times y is y squared. The square root of y squared is y. Or if you think of it as a square root times a square root, we'll cancel out the square root and you just get 5y. Now, I am finished. I have nothing else I can do because if you look inside the square root, actually, just kidding, I do see something that I can do. Do you see how it has the square root of x squared? I can simplify this a little bit better. The square root of x squared is simply x. So what I actually get now is x times the square root of my leftovers on the inside, 5y, divided what's left over on the outside, 5y. Now, I want you guys to notice here that it looks like the 5y's can cancel. However, the top 5y's on the inside, the bottom 5y's on the outside. So they are not the same type of numbers, so you cannot cancel them out. But this equation is the exact same thing as this equation. It's the exact same value because all I did is multiply it by 1. But look, the denominator is no longer a radical, which means we have rationalized the denominator. Now, how do you do it with a cubed root? Well, remember that if I write it as one big cubed root, that's technically the same thing as the cubed root of 2 over the cubed root of 3x. And there's nothing I can simplify there. Nothing simplifies in this fraction, and there's no cube roots I can take of things. So I'm going to approach it in a very similar way to up here. The problem is up here was a square root. You only need 2 of a kind to create a perfect square. But for a cubed root, you need 3 of a kind. So what I'm going to do is I'm going to multiply this by a fraction, and I'm going to multiply it by the cubed root of 3x. And whatever you do to the bottom, you got to also do to the top. But I'm going to do it one more time. Why do I do it one more time? Well, in order to cancel out a cubed root, you need a 3 of a kind. So if I say the cubed root of 3x times the cubed root of 3x times the cubed root of 3x, you know what I get? 3x. The cubed root goes away. Now I forgot to fill out this one. If the cubed root of 3x is on the bottom, the cubed root of 3x is on the top. And technically I'm just multiplying by 1, and then I'm multiplying by 1 again, because anything divided by itself is just 1. But the reason I chose this is because I've got 1, 2, 3 of the same kind of cubed root. That cancels out the cubed root. My denominator is no longer a irrational number. So now we just got to finish up with the top. What's the cubed root of 2 times the cubed root of 3 times the cubed root of 3? Well, 2 times 3 times 3, 2 times 3 is 6, times 3 is 18. So we have the cubed root of 18 on the top. And what about the variables? We have x times x. Well, that's x squared. And you can check to see if it's simplifiable, but 18 is just going to break into a 2, a 3, and a 3. So there's no triplets of any kind. And you cannot simplify the 18 and the 3 because 18 is an inside number and 3 is an outside number. Same thing with the x's. These x's are inside, these x's are outside. You cannot simplify them. There's nothing I can take the cubed root in here, and so it looks like there's nothing else I can simplify. That would be your final answer for rationalizing the denominators. So recap, if the denominator is a square root, you need 2 of a kind to get rid of the square root. If the denominator is a cubed root, you need 3 of a kind to get rid of the cubed root. Same thing goes for the fourth root. If the fourth root is the denominator,